freak me out. Okay. All right, if there's no questions, let's try an example out from Newton's method. And if you have your little sheets, I think I'll do this, like on the test, I'm going to go ahead and give you Newton's method, the equation, right? So everybody got one of these from last time? Well, you have it? Yeah. Sorry, hey. Get excited. Thank you. Go ahead. Alright. What was I about to do? I forgot. Just something, right? I wasn't even saying what I was about to do. Oh, yeah. So, I'm going to give you this. And last time we didn't get to this point, but here's what it is in general. Is everything in the right place? Yeah, Jeff. Almost. Sure. So, one way to look at this is xn is your current guess, and then if you run it through this process, it tries to refine that guess. That's one way to look at this. Do you guys understand what I mean when I say that? Little tiny bit. Now, if you weren't here yesterday, you get to suffer through my, because I'm not going to pull it back up on that stupid computer and wait for it to. So the whole idea is I'm trying to find this root. And you have to understand that I have a graph up on the board currently, because some of you guys would go, it's right there, next section. But no, so I want to get the idea of why this process works by looking at it visually. And when we do this process, we don't have a graph to look at. We just have a function to work with. But the idea of it is, if I can come up with a decent first guess. So this is x1. Then I create the tangent line going through the point x1, f of x1. So that tangent line would be something roughly like that. This will be my next guess, x2. And then I do that again. I get a tangent line. So now it's like, you can do it, Jeff. That, look at that, I'm getting closer and closer. That's the idea, I'm getting closer and closer. Now you can tell this has serious pitfalls. If my first guess would have been right there, oh my God. If that would have been my first guess, then the tangent line would have taken me away, right? Just far away. I wouldn't have come back. I have to come back to the x-axis to get another guess. Also, if my first guess is on the other side of this thing, it's going to take me that way. I'm going to find the root that I don't want. The other root. I don't want that root necessarily. I'm trying to find that root. And we saw that. I can't remember if I showed you that or not. But you can see how that can happen. Are you guys kind of with me? The better your first guess is, the better the whole thing works. I like it. So, an example of an evil root would be a root like that. So if you guess this, the tangent line is going to, well, it'll still work, but it won't, as you get closer and closer, well, actually, that'll work. What am I trying to think of? Now that's fine, that'll work fine. I can't remember which algorithm that doesn't work for. Okay, well, it's a bad example. So up here it won't work, it'll take you far away. There it'll actually work. I can't remember what algorithm it was that doesn't work for screw. So let's do, does anybody have an example from homework you want to try? Or I'm just going to pick one out. Yes. I didn't bring my darts with me. Let's see. Here we go. Let's look at this. Let's do one with, yeah, let's do this one. That's gross. So here's an example. It's number 18 in section 4.8. All right, so let's try to do. Let's try to actually take a second. Take several seconds and try to graph a rough sketch of this, and on top of that, a rough sketch of this. Without a calculator, that's the idea, right? We are the calculator. We are calculators. Like some of you guys are looking at me like, I am not going to do that. All right, I can't, you know. You bring a student to class, but you can't make them do shit. All right. It's a new adage, the old saying. Let me make sure everybody's on the right track here. What's the domain of this thing? It's a bad start. What's the smallest x can be? Negative 1. Because what's the smallest number you can have inside a square root and not get unreal? 0. So 1 makes the inside 0, negative 1. So negative 1's the smallest it could be. Everything after that's fine. So if you're going to draw a rough sketch of a function, you have to have some idea of where the function exists. Otherwise, you ain't going to be able to draw a rough sketch of the function. You better make it. I like that. It's a good use of that phrase. But so negative 1. And then at 0, it's 1, right? And then it just kind of goes from there. Wee-haw! Okay, so it doesn't have to be perfect, it doesn't have to be beautiful. We could make it a little bit better, but oh well, I'm not going to. What do we know about this guy?
It's an upward parabola.
Cool, and now become more specific. Become very specific. What are its intercepts? The x-intercepts?
1 and
Yeah, 0 and 1. And then it's upward parabola, right? So then it's going to be, looks like it's going to be pretty tight. So let's see. So let's say I want to find this intersection. Is that cool? You guys kind of with me? Let's see if this is good enough. The worse our functions are, the better our rough sketch needs to be. And these two functions are nice functions. They're parabola and a radical. It's nice. They're nice. So what's a good first guess then? Well, let's see. That's 1.
1 and a quarter.
Sure, 1.25. There's some bigger than 1, right? It's on the other side of 1. It's probably something bigger than 1. So I'm going to let x1 be 1.25. So now, to get this process going, I know what my x1 is, 1.25. What do I need to figure out to set this algorithm up?
what it is at each point.
So what is f of x first? We've got to figure out what f of x is, and then we have to figure out what f prime of x is, and then I can plug stuff in. I like it. So what's f of x? How do you want to write f of x? Does somebody remember what I said earlier? What does Newton's method do? It actually finds roots. Now I really want you to make this transition. It's much easier to graph this and this on top of each other than it is to move this over and then graph that function. Good God. But if I did move that over and graph that function, what's going to happen roughly right here? What's that minus that supposed to be? Well, I think that's about where they equal each other, so it should be about where the function is 0. That's what Newton's method does. It finds the zeros of a function. So where these two are equal to each other, or where they equal 0, if I move this dude over. Please let that make sense. Newton's method finds roots. So what's it got to do with this shit? Well, move that over, find the root. It's where they equal each other. Okay. So then we get how you want to write it. It's up to you. I probably would rather have the radical piece be.
Square root of x plus 1.
Doesn't matter. Yeah, so let's do that. That's the first thing here. Square root of x plus 1 minus x squared plus x. Is that cool? Just subtract that over. Alright, so if I subtract it over, I'll have a function equal to 0. That's what Newton's method does. It'll find the roots for this function, and that's what the equation wants me to do. Yes?
Is that 1.25 encircled your guess?
Yes.
Okay.
Cool. My first guess to find that solution. I like it, because there is another solution back here. Okay, cool. So, alright, so what's f prime?
1 or
1/2 x plus 1 minus
negative.
minus
Square root plus 1.
plus 1.
Alright, cool. I like it. How we doing? Okay. So let me show you how to incorporate what I need to see as work, because if you were here yesterday, I'll do this up on the overhead again. But as work, I need to see you set up the algorithm, and then you could put your guess, enter. Record all your stuff in there until it starts to not change, right? So let's try this again. Try this out. It's good to know how to cuss in several languages.
Yeah, but
What's up? I can cuss in sign language. I love it. It's a really good way to get frustration out. In a meeting, screw you. Hey. Okay. Sorry.
Or just do this. It means bull.
It means what?
Bull.
Bullshit?
Yeah.
Okay. Alright, guys. So how do I write? So what I'm going to do is I'm going to write this. You could even put a little ANS instead of XN, but I gotta just use XN since it's in there. So what's this going to be? This is going to be XN minus, what goes on top?
Square root x plus
Yeah, square root of xn plus 1 minus xn squared plus xn. Oop, get out of there. Over f prime of xn, so it'll be 1/2 xn plus 1 to the negative 1/2 minus 2xn plus 1. Let me stop right there. So when I want to build this in the calculator, I do like we just did the other day, and like I illustrated on that handout. So if you know how to borrow a calculator, there's some here. Somebody need a calculator? Yes? Alright, there. Is there a reason for me to open my cooler? Like he's squeaking. Sorry, but yeah, he's really gonna throw that shit. All right, I see. Okay, I should switch it over. Turn this guy around. Okay. Alright, so here we go. Let's try this out. This is not in the way enough. Alright, so there's yesterday's party up there. Let's see. Alright, so here's how it goes. What gets me started? What do I put in there? Very first thing.
1.2.
Beautiful. You got to give it something for A and S to represent. So if I put 1.25 in, enter. Now this, right above the negative key, that A and S is temporary memory. It holds the last thing that was on the screen. So if you do something with it and hit enter, now it's going to hold that new thing that's on the screen. It's going to hold that. That's the key to what makes this work. So every time I do this, as I showed you on that earlier horrible picture, if you were here yesterday, you saw the better computer one. It gives you another guess, it makes a tangent line, it gives you another guess, and every time you do that, it's getting a little better, a little better. Alright. So here we go. So we put, everywhere you see an XN, you can put ANS. I know, I planted that seed, and that's probably not the best way to even say that, but I'll. Minus square root, where we go? answer plus 1. So I'm just putting it down. Now be careful. You want this parenthesis around the top, and then you need a parenthesis on the bottom because the calculator does not have eyeballs yet. I'm sure the TI 3000 will. And then it's Arnold, and then the whole thing. Skynet, yeah. So I don't want to close this parenthesis until I'm done with the top, right? So what do I got? Minus answer squared. What was it? Plus answer. Now I can close that. Divided by parenthesis. Half times NS plus 1. Get out of there. To the...
Negative 25.
Yeah, negative 0.5. Thank you. Blah, blah, blah. Minus twice the answer. Plus 1. So there's a little... You got to understand. So that is really almost impossible to check. Your brain goes, sure, why not? So there's a little bit of precaution you got to take when you first build it, because the beautiful thing is it took a while for me to put that in, but now it's going to be like bam, 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 right? That's the whole idea. So let's see what happens. Let's see if we get a good first guess. Get out of there. Java update. Bam, 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 bam. Okay, I can stop. Right, so our first guess was 1.25. So when it came down and it made the, well, this is not even the function we're talking about. So whatever this function looks like, when it made the tangent line, it actually took me over to 2.268, whatever. And then when it did it again, it took me back to 1.94. So I liked it. Maybe. So the actual answer, roughly 1.9 almost. How we doing? How do you check that? Just put the function in your calculator and let the calculator do the work, right? And again, this illustrates why it's such a dumb comment to say something like, well, my calculator does it already. Well, what does it do? We should know the math. We're the ones who made the calculator. It didn't just drop from the sky, aliens came, use this. No, we programmed the calculator. So you guys should be like, well, I should be able to know that shit. It's just humans did that, so I should be able to know the math. Well, okay, now that we've got 1.897, blah, 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 let's check. So I put the function in. Oh boy, let's see, square root of x plus 1. Let's see, what else was it? Where'd it go? Minus x squared plus x. Yahoo, is that what? Hey, graph, let's see what kind of weird ass. Yeah, I got a weird freaking Zoom 6. So that's what it looks like after you subtract those things. Sure, why not? And so right there, I want that root right there, right? That root. So I hit second calc 0. Like I told you the other day, I reminded you it wants a left bound. So be to the left of the answer, a right bound, be to the right of the answer, and now your guess. 1.897, what we got earlier, right? Is that cool? And now you can understand why those bounds are there, because if it did go up and then go over and it was way outside of those bounds, it would, like I said, it would modify your original guess so that it ends up inside that bound. You understand better why it's asking you for left bound, right bound now, or you should. It should make sense now. Cool, I like it. Maybe. This is the work. This is the work, along with a rough sketch to tell me why you pick what you do. So together, that's the work, and then you just copy down the numbers you get on the screen of the calculator when you do the whole thing, enter. You guys understand? So let's let me show you something. What if somebody give me a bad guess?
7. 6 points.
I love it.
Damn.
Oh shit, that one. So if I hit 7, enter. Now that's in my answer, right? So if I hit second, enter. Or if you got the newer calculators, you can just hit the up arrow to pull that back up. And now if I do my whole process, it'll start with 7. Let's see what it does. Hey, look at that. It's coming back. Cool. You see that? Because again, if I look at my function, 7 is a really bad guess, but look what happens. If I choose 7, it's going to make a tangent line to this. It's going to take me, hey, it's still going to manage to take me back. In fact, let's try to pick 70.
Pick like 0.
Oh yeah, so anything that's closer to the other root is going to pick up that root, right? So now we can, even from our graph, a good guess for this would have been just below 0, right? So before we do bad guesses, let's do a good guess for this other root. What's a good guess for that other root?
Negative 0.5.
Negative 0.5? Sure. You can click back up. Thank God I don't have to put all this crap in again. Enter, enter, enter. Okay, I'm already there, right?
Yeah.
Negative 0.48, sweet. And again, you can go back, you can double check it by giving the 0 of the function in your calculator, no big deal. That's just not good enough to do the work, but it's good enough to check the work all day long. Yes, sir?
How do we know which one to take? Like which root to take? Are you going to specify?
This problem said find all the roots.
Oh, so do both.
So when you do your rough sketch, your guess, you want it to be close enough to one and definitely far enough away from the other one so you don't get freakiness there.
Okay, so
Right.
say which one to take.
On the test, I'm probably going to tell you the positive or something just to
Okay,
so you're not
normal.
taking all day long to find all 7 roots or something.
Okay.
Yeah. In case it's got 7 roots. I like saying roots. All right. Let's see. So if I did try 0, is that what somebody suggested? Let's see what happens. There you go. Sweet. You got to it. All right. So I just can't try anything that's out of the bounds of this. So you can imagine that if I have something that's basically down parabola, any negative guess is going to shoot me back up. I don't know if you guys see that. The tangent line is just going to shoot right back up and make it better. So it's almost impossible to get a bad guess on a nice function like this. So there are functions that are almost too easy to have bad guesses for. So those exist. So you want to make sure your sketch doesn't have to be perfect. And I know a lot of you guys are just going to plug it in the calculator. What can I do about that? I don't know. But you desperately want to try to just do this by hand. Make this your own. Say, calculator, that's nice. You can do this shit. So can I. So you guys like, no, Jeff, no. All right, well, what can I do? Okay, so any questions about Newton's method before we get into the next section? No. You guys feel okay about Newton's method? I mean, compared to some of the other stuff we've done, Newton's method is not that bad, especially because I'm going to write this down for you on the test. I'm not going to make you memorize that. Partially because I don't have it fully memorized. I don't know if you guys picked up on that. I'm never going to make you memorize something I don't have memorized. Okay. So like a PE teacher that makes you do push-ups, and they can't even do push-ups themselves. I had several of those.
Did you ever rebel against it?
No, I was too big of a geek. What's up? Yes, sir. All right. So I think I've asked, at least once in a bonus question, I asked you something like this. Given f prime, can you tell me what f was?
Oh, yeah.
Oh, yeah. So to start off really easy, if you know that f prime was 4x, what could f of x have been? 2x squared, 11. Now, really pick up on what's important. So, go ahead.
Plus C.
Okay, good. I like it. So we're going to fold that in here in a minute. The most important part about this is the x piece. The constant matters to the point where you got to make sure it's still there, but it doesn't matter in what you're thinking. Where would something x to the first power have come from? Of course, it would have come from x to the second power. Yeah, exactly. So when you have a polynomial function, that's pretty simple, right? And if it was x squared, there must have been a 2 out there, so when that 2 comes down. Now, Troy's point is this is not the only possible answer because What could have been here that would have disappeared after I took a derivative? Any constant you want. So we represent that normally as plus some unknown constant. Alright, stop there. Does that make sense? So some of you guys who've had any calculus before, the bane of your existence might have been forgetting the plus c when you did these things, right? So we're headed that direction, right? But 4, 9, I can't remember now if they make a big deal out of plus c. Yeah, they do, sort of. Okay. Let me give you another one here. What about if the derivative was 3 sine 6x? What would the original function have been?
So 3 is a constant.
Think about it for a second. Don't say anything out loud. Just I want everybody to kind of think about it. Somebody's going to say it in a second. I'm not going to think about it. But think about it.
I gotta process this.
Okay. What sucks about sine and cosine, this is going in reverse, and I can hear the gears, I can smell the smoke. It gets really difficult, because what do? What's the derivative of sine? Derivative of sine is cosine, right? But what's the derivative of cosine? Negative sine. So I wouldn't have taken the derivative of a cosine to get here. I would have taken the derivative of a negative cosine to get here. Do you guys see where I'm starting? Now I worry about the numbers. Please, dear God, be to the point where I know that's got to be that. I mean, the inside of a function does not change when you do a derivative. But what had to have been here? Because what would happen when you took this guy's derivative? What would kind of come out? A 6. So there must have been a 1/2. So when the 6 comes out, it would become a 3. Do you guys see how to think about that? It's backwards thinking, which sometimes hurts. But the better you know derivatives, the easier this is going to be to do. So not remarkably, the name of this thing we're doing is the antiderivative. All right, so these are become an I. Derivatives. Jeez. It's just not the daily I. Okay.
Is this integration? Is that the same thing?
No, not quite yet. We have to prove the connection. Integration officially is finding the area under a curve. So like if I had, if I have a triangle, I can find the area easy. But how do you find the area under a curve? Well, calculus does that for you. So finding this area. The thing that some teachers gloss over that is important, and your teacher is freaking, what the freak? He wants to show them. I'm going to try to make the connection between antiderivatives and the integral. They're not just automatically connected. It's actually not something that was obvious back in the day. You have to make that connection. Thank God there will be a connection. Now, what have I left off here to make this complete? Beautiful. So any constant you want.
Would you mark this down or pointing to get plus c?
Yes. Because then, is it right?
No.
Okay. So, you should lose points if it's not right. Sorry.
If you tried to do another antiderivative, would you have to make it c squared?
I like it. So all right, let's try this out. You ready? So let's push this a little bit, and we'll use. Well, I could have used what I just have at all. Let's say I know that f double prime of something, and this is more like the bonus I had. Let's say f double prime of something is what you got, John? 6x squared minus. Let's make it gross. Yeah, I like it. Minus x. So what form would f prime have been in? It would have come from a what? Third power. So you're sucking that 3 back up there. It's one way to think about it, right?
So 2x.
So there must have been a 2 there, so when the 3 came down, it was a 6. Does everybody get that process? That is the thought process you go through. Now this is neat. That would have come from an x squared, so what must have been out front?
1.
So that would kill the 2 that wants to come down. And then, of course, to make it complete, plus c. Right. Let me stop there for a second. Is everybody cool with what's happened so far? I like it. Cool. All right. Let's take one more step. All right. What must f have been? This is where things get weird. Yeah, I like it. So this would have come from the 4th power. Therefore, that must have been a 1/2, so when the 4 comes down, it becomes 2. Am I even thinking about this anymore? Of course not, because this goes from there to there, and then I'm worried about this to there. I don't care about this anymore. That's a derivative removed from what I care about.
That's so fascinating.
What happens here? This would have come from x to the third. So in addition to this, it must have been a 1/3. So overall, I would have a 1/6. I like it.
And plus C.
Keep now plus c. Say it. X plus. What do you think we do? Plus d. Exactly. You know math, people. What do we do? Well, using x. Got another variable. Y. So that is what we do. We either use C, D, E, F, or we use C1, C2. Oh, screw that. Let's just use C and D.
But you still would need the CX if you go on from the second derivative.
Yeah, because if I didn't have that there, the derivative of that wouldn't be there anymore. So you got to think, why is it here? It must have had an x on it so that it's still there after a derivative. If it's a constant, it would have died. It would have been gone. But it's not gone. Could not have been a constant before. Must have been a linear function of x. How do we feel about this so far? I mean, this isn't, the better you know derivatives, the easier this idea is. Now you can imagine there are functions that we cannot do this to yet. So when we get into the next section, and then if you go on to the next class, you will basically